Bismillahirrahmanirrahim. Assalamu alaikum. Hello everyone. Today we are going to discuss about free body diagrams. Okay. So as we already know, free body diagrams are one of the most important initial uh, part of the solution of any problem. And based on the free body diagram solution, you can tell that you will be able to solve the system correctly or incorrectly, because if your free body diagram of the system is drawn incorrectly, you will never be able to converge to the correct solution of the system. And if you are able to draw the FBD of any problem or system correctly, they say that you have already solved 50% of the problem or numerical of that system correctly. Okay, so free body diagram is a very important aspect from the system solution point of view. Okay, so it is very important. So you have to be really good in drawing free body diagrams of structures, whether in statics, in dynamics, solid mechanics, vibrations, whatever subjects you are studying, you have to basically be very well, uh, have a very well understanding of drawing FBD of structures, and for that you need to have a good understanding and knowledge of equilibrium of a body in 2D and equilibrium of a body in 3D. Okay, these are very important. So after this, we can say that here is some practice problems which are solved correctly, so that your understanding may further be enhanced. Here they have given you a truss, and they say that the weight of the truss assumed negligible compared with P. Okay, it means that the force of the P, magnitude of force P is so high that the weight of these components, individual components of the truss, are negligible, are very small compared to the huge magnitude of this force P. So we will not consider the weight of these truss components. So if you look at it, this is a pin. Pin is showing two reactions. Roller is over here. Rocker is over here. It is showing one reaction. Okay. A cantilever beam which is fixed in a wall is going to be. These are basically the external forces. This P was also an external force, and these are basically these red AX, AY, and BY were basically internal constraint or internal supports reactions. Okay. So a fixed support, if you look at it, you know a fixed support will always have three reactions. So vertical V, horizontal is basically F reaction is a horizontal, and moment is M. Now again they say beam is over there. Beam smooth surface contact at A. Okay, there is a smooth surface contact at A. Then there is a couple moment over here. They have shown you, and then there is the horizontal force P over here, and they say smooth surface contact at A. Okay, and then there is also a pin over here also. So for a pin, you can see that you will have two reactions at B. The pin is there, By, Bx. Okay, and again the weight of this beam is going to be acting at exactly at the centroid of this rectangle, which is this one. Again, this is the moment. You can draw it like this also, or you can also draw a couple moment over here also. And again, smooth surface contact at A will always have a reaction perpendicular to the surface at the point of contact. Okay, and you can see this reaction N is perpendicular to this beam, making an angle of 90 degrees. Okay, so this is practice problems, and I hope you understand this. Again, another problem: rigid system of interconnected bodies analyzed as a single unit. Okay, weight of the mechanism is neglected. Weight of these links are neglected. So a roller is over here. One roller will give you one reaction. A pin is placed over here. It will give you two reactions. Then this weight M, this mass M. So it is being connected by means of a cable. So this is going to be mg, and the tension in the cable will be equal to W, whatever mg is equal to. Okay, so this is how you basically draw FBDs. Okay, so this is already shown correctly to you. Let's do some more challenging FBDs, which will help you understanding further. Okay, so now they have given you incomplete FBDs. This is the body. They say the information about this system is bell crank supporting mass at mass M with pin support at A. So there is a bell crank which is supporting this mass M and it is pin connected at A. Okay, so here is a lever which is having a tension T. This is a cable, so cable will always have a tension T. Okay, the mass is over here, so mg is going to be placed over here. Okay, and then there's the pin over here, so you need to put two reactions over here for the pin. The pin will have two reactions, so you can if you want, you can have one reaction here and you can have another reaction here. Okay, one reaction here and one reaction here. Okay, so again go to another problem. Control lever applying torque to shaft at O. Okay, so there is a control lever which is applying torque to the shaft at O, this control lever. Okay, so it is pulling over here and it is being connected to the shaft at O, which is being fixed with a pin. So again, this is a vertical reaction shown. You also need to show a, because since it is a pin structure, you need to show another reaction over here. Okay, so pin has two reactions. Okay, uh, beam OA of negligible mass. This is beam OA of negligible mass compared with mass M. Okay, this mass is negligible compared to the huge mass M. Boom is hinged at O. This boom is hinged at O and supported by a hoisting cable at B. Okay, it is hinged at point O and there is a hoisting cable which is basically connected by a cable this. Okay, and this is hoisting cable which has tendency to rotate. It's like a winch. Okay, so this weight is basically given as mg over here, and this cable will have a tension T, and again there is a basically guiding point over here that the boom is hinged at O and this is O. So hinged means there will again be how many reactions? If you can see, there will be hinge will always have a hinge and a pin are exactly the same. Okay, practically they are installed separately different, but they will all have these two reactions. Okay, at O. Okay, now go to a problem with some frictional effects. Uniform crate of mass M leaning against smooth vertical wall. Okay, so there is again smooth vertical wall. So this is a normal reaction of the wall, and there is no friction on over here because the wall is smooth and supported on a rough horizontal surface. Okay, again the weight is acting downwards. Okay, and this surface is over here lying on the ground. This is the normal reaction B. This is the weight. This is the reaction of the normal reaction of the wall. Remember that the wall is smooth, so there will be no frictional component. But they say rough horizontal surface. This is very unique. Since the surface is rough, so there is a component of friction. Okay, so the component of friction has always needs to be placed correctly. So if this crate is going to slip, it is basically going to slip basically in this direction. Okay, it is always going to slip in this direction. So, which means if we can draw, if it if slips, it will always, the slippage will be like this. Okay, the slippage will be lying it on the ground exactly something like this. Okay, so first it is placed like this. It was placed like this. Okay, so if you look at it, it has further slipped down. You can see it has further slipped down. Okay, so it is going to slip in this direction. It is going to slip in this direction. The frictional component will always try to prevent the motion of this crate. So this is going to be your frictional component. This will be your what is called as the frictional. This is going to be your frictional force FF. Frictional force FF. Okay. Another example over here we have is loaded bracket supported by pin connection at A. Okay, so this bracket is supported by pin connection at A and fixed pin in smooth slot at B. So there is a fixed pin in a smooth slot at B. This slot means that this pin is able to move along this slot. It is basically adjustable. So since this pin cannot move vertically in this direction and in this direction, it can only move around the space of the slot. So it will have only one reaction, which is correctly, even though it is saying it's a pin, but again it is an adjustable pin. Here over here, it is the load is placed, and this is the basically pin connection at A. So this pin connection means that it will again have two reactions. So you can have one reaction here to complete this FVD, but the pin has always two reactions. So you can put another reaction over here also. So these are just examples. Hope you will be able to, you would have understood how the basically structures FVD is basically being completed. So I thank you all. Hope you have understood the concept of FVD and how to complete FVD. I thank you all, and I hope everyone will have a good day. Before leaving, I am requesting everyone to subscribe to my channel and so that, and also click the bell icon so that they will be able to see more knowledgeing and interesting videos explaining the engineering concepts and its implementation in engineering structures. I thank you all.